Emma, and I like ham radio. Today we're going to learn about resistance.
So we've talked about the force that motivates electrons, which is
Voltage.
And we've also talked about the flow of those electrons once they're moving, which is
Current.
Sometimes those two things together can cause a problem.
What do you mean?
Well, when electrons get excited and start to flow, they are usually flowing through a material like a copper wire. Sometimes so many electrons try to move that the material can't handle all of them, and then pop!
Yikes.
In the electronics field, they call that letting out the magic smoke.
Magic smoke?
Well, yeah, when smoke comes out of something electronic, it stops working. So as long as the smoke stays in, it keeps working. There must be something magical about the smoke that keeps the device running, right?
I get it.
Yeah, I'm just kidding. Actually, when there are too many electrons rushing through a material, it can make it burn up. That's where the smoke comes from. It's not very magical, and it usually stinks.
Ooh, I know that smell.
Now, if only there was a way to slow those electrons down. So far, we've learned about conductors, which allow electrons to flow easily, and we've learned about insulators, which won't allow electrons to flow at all. We need something that will allow electrons to flow, but not quite so fast. Instead of a stop sign like an insulator, we need more of a speed limit sign.
We could use a resistor.
You're right. You've used those before, haven't you?
Yeah, when I use LEDs, they have to have a resistor or they're blown out.
Exactly. The resistors that Emma is talking about are parts of an electrical circuit that resist the flow of current and create resistance. Basically, they make it more difficult for electrons to get through the circuit.
2 runs and 2 lots of 10 points to her credit. Can Maria make it a triple treat on Gauntlet? Rio tries to put the brakes on, but Maria bypasses her with ease. Rebel Steve.
To put it all together, voltage tries to push the current through the circuit while resistance makes it harder to get through. As you might have guessed, we can measure resistance. Do you remember what unit we use for resistance?
Ohm.
Yeah, it kind of sounds like you're meditating. This is also the first unit of measure where the symbol for it doesn't use an English letter. The symbol for volt is V, and the symbol for amps is A, but the symbol for ohms is this.
It looks like an upside down U.
This letter comes from the Greek alphabet, and it's called an omega. A capital omega, to be specific. The lowercase omega looks like a W.
Omega.
You can kind of see why they picked that letter, huh? It sounds like ohm.
Yeah.
So what do we use to measure resistance?
Same thing we use for everything else, a multimeter.
You're right. However, what specific function of the multimeter would we use to measure ohms?
How about an ohm meter?
Yep, an ohm meter. It's got some neat tricks up its sleeve too, but we'll get to that later. First, we're going to talk a little about a cousin to resistance. That's a little more complicated.
Resistance has a cousin?
Yep. It also starts with an R and also wants to stop something from happening in the circuit. Only in the case of reactance, it wants everything to stay the same. Reactance doesn't care what the voltage is or what the current is as long as you don't change it. If you try changing it, that's when reactance starts trying to prevent the change.
So you're saying it doesn't like change. I know people like that.
Me too. Do you remember the 2 types of current?
Yeah, direct current and alternating current.
Well, reactance is a problem for one of those and not really a problem for the other. Can you figure out which one?
I'm going to pick alternating current because it changes direction a lot.
Good job. Most of the time, reactance doesn't do anything in a direct current circuit because the current flows in one direction at the same rate and the same voltage. In an alternating current circuit, it's a whole different story. The voltage and current is always changing, so reactance starts acting like its cousin, resistance, and starts resisting the change.
Hey, stop changing.
There's one other similarity that these cousins share.
What's that?
Their unit. Do you remember what the unit is for resistance?
Yeah, ohms.
It's the same for reactance. Ohms. In fact, when these two get together, there's a name for it. It's called impedance. The root word there is impede, which means to hinder or interfere. These two get in the way of current flowing.
I see.
Okay, so I have to tell you a funny story from when I was still learning some of these things myself. It's partly the reason I'm teaching you about impedance, other than you might run into a question or two about it on the test.
I like stories.
So I wanted to know what kind of cable I needed to connect my radio to my antenna. When I searched the internet, every article related to ham radio told me that I was supposed to buy 50 ohm cable, not the 75 ohm that they use for cable TV. Now I knew that the resistance of a wire increases the longer it gets. I needed a cable that would come out of the radio and go up to the top of a 50-foot tower. I could not, for the life of me, figure out how I was going to make sure that that long cable was exactly 50 ohms. I think I might have even got out my multimeter and tested a section of wire. Finally, after I did a lot more reading, I discovered that impedance was also measured in ohms. So when they were talking about 50 ohm wire, they were talking about the impedance, not the resistance of the wire. I guess I always thought anything measured in ohms just meant resistance.
They should have used a different name.
Yeah, that would have been more clear. But in this case, it's not about how much the wire resists the current, it's about how much it impedes changing current, like the radio waves it will be carrying. Well, now you know something I didn't when I started out. Buy the 50 ohm impedance not resistance cable. Actually, I might have some cables we can go measure.
Let's get hands on.
Alright, here is my cable. We can measure a cable. Not that this is going to tell us the impedance of the cable, but it will tell us the resistance of the cable. So let's turn on the...
And we have it set to the right setting right now, but that's the setting you'll need. It's 200 ohms.
Right.
Yep.
I'm not expecting the cable to have much resistance at all, so that's why I have it on 200 ohms. Alright, ready? Go ahead and put the...
So, black on one side. It's not polarized, so it doesn't really matter.
Yep.
You just touch into these little copper things.
Yeah, to the little center pin there. See if you can get it to read.
Is it working?
Should. You might have to press harder.
Here.
Yeah, I do it with my fingers. Yep. Since it's not, it's not powered right now. We should not have any. There we go.
Oh, there we go. Oop. It's being a little finicky. Doesn't want to be measured. It's like, no, don't measure me.
Yes.
Please.
So once you have it on there.
Come back here. Give me a little bit of a hard time.
There we go.
There we go.
And it's gonna fluctuate around there a little bit, but
yeah,
we're looking about.
It's also how tight I hold it on there too.
Let's just say it's very, very few ohms.
Yeah, because that's the 200 ohms, not even kilo ohms.
Now, when we want to do resistance in electronics, there is a device that we can use for that. Actually, little components that we have. Resistors. Okay, I just have some random resistors here from my my kit here.
So I'm gonna.
So you can grab one out and check it.
Grab one.
Now you'll see that you could cheat, and if you knew what those color bands mean,
I don't. I haven't memorized that
you could tell it. You could find out what the resistance should be. But we'll talk about that in a future video.
So I don't know if you can see, but the colors are going from here. I'll switch it around here. going from right to left are green.
Or left to right.
Oh, right. Left to right are green, blue, brown, and gold.
Right? And we'll talk about what that means. But then there are some people out there that have that memorized and can tell you exactly what that resistance should be. You don't have it memorized, do you?
I think I know.
All right, let's put it on the but let's measure it with
let's see if I'm right.
What do you think it is?
Well, I think I've memorized it enough. I think it's 56. I don't remember the third band.
Okay.
Well, but the first two color bands are 56.
Okay, let's check it out. You might have to hold it with your fingers.
Yeah, looks like it will.
Well, it's more than 200.
Well, there we go.
It would be close 542 or so. That's pretty close to 560, isn't it?
Yeah, it is.
So yeah.
Oh, that's right. The brown is 10.
Good job.
Yeah.
So that's a resistor, and we'll learn lots more about resistors in a future video. But in that video, we'll talk just about resistors because they're an important part of electronics. But for now, we're just kind of measuring some different materials and different things that have different resistances. So the next thing we're going to do is we're going to do this, a pencil.
But why is it sharpened on both ends?
It's sharpened on both ends because we want to touch the graphite in the pencil.
Oh, that's the stuff that comes off.
Yeah, that's stuff that you write with.
Okay.
And so that way you can touch the leads to the graphite in both ends. So let's check and see.
That makes sense.
So graphite is conductive. And so...
I might get some graphite on my fingers.
That's okay. There you go.
Doesn't have much. It doesn't let much flow.
Actually, it's pretty good. Actually, 45 ohms. There are some resistors that are in the thousands. This would let electricity flow pretty well.
Yeah.
Okay. And the last thing we're gonna do is has the potential for being messy, but we'll be okay.
Okay. Good. A canning jar? What?
Canning jar with water in it.
Oh.
Because water is conductive.
Let's test it.
Let's test it, yeah.
So we stick both leads in the water.
Yep. Now in this case, water is not that conductive, so we're going to bump it way up to the top here.
Ah.
Okay, let's see what we can get here. There you go.
Look at that.
So that proves that electricity is flowing through the water.
Whoa. So that's why you don't want to let water get near any of your electronics.
Now, there's also another thing you can do to water that makes it more conductive.
So we'll get out the other canning jar here.
Yep. And here's the other water. Looks about the same, right?
Yeah, what's different?
The bottom jar is salt water. I put a bunch of salt in there. So let's test the difference. As a general rule, salt water conducts electricity better than regular water.
Look at that. Here,
Yep.
we can compare them better. So we do this.
You gotta get your hand out of the way. So we're somewhere in the hundreds to 200s. Okay. I'll go to the other one. There you go. It's less, isn't it?
It's less, isn't it?
Yeah, so there's less resistance. So that means that it conducts better. So the more resistance means the more it resists the flow of electricity.
Yeah.
So if I were to take a piece of wood, actually let me take the pencil again.
Mm-hmm.
And if I measure like this, oops, nothing, right?
Yeah.
That's because wood does not conduct electricity, right? And so
Or
it has...
Here, even better, because this pencil, I think, is coated. We just touched the...
Yep. You want to know something? One last thing that is conductive?
What?
Me.
Oh.
Your skin conducts electricity. Yeah.
That's weird.
And then there are products out there. In fact, there are scales that will use the resistance in your body to kind of determine how much fat is in your body versus how much muscle.
Huh. Cool.
Neat, huh?
Yeah.
One last thing we do have to talk about is multimeter safety.
What's that?
Okay, so let's talk a bit about how the multimeter measures the resistance.
Mm-hmm.
So inside the multimeter, there is a little, I believe it's a 9-volt battery.
I think it is.
Okay,
Yeah.
so when you have it switched over to the resistance mode, okay, to measure resistance,
Mm-hmm.
these 2 leads or probes will give off a very tiny amount of electricity.
Oh.
They'll have some voltage between them, okay?
That's how it can measure how much
Yeah.
is going through.
And so that's actually a really neat thing that you can also use an ohm meter to do, okay? You can use an ohm meter to find out whether something is connected.
Oh.
So if you have a wire and there's a gap in there, if there's a gap in the wire, what would you expect to see on the meter?
1.
Right.
Because it doesn't conduct
It wouldn't conduct at all.
anything. So it'd be an insulator.
Right.
Either it's got a break in the wire, which then the insulator would be air, or it's got something else, like fabric or something in
Right.
the way of the 2 pieces of the wire.
Now, what would happen if you put your meter on both ends of the wire and it showed a very low number? Would you have a circuit?
I
So
don't
if
think
1 means the circuit is not connected,
Okay.
what does a low number mean?
Yes.
It means that it's flowing, right? So the little voltage that's coming out of the probes is going through the circuit to the other one, okay?
Ah.
And that means you have a good circuit. So it can be used to test circuits, okay? Now,
Cool.
when we're doing circuits, though, one of the things we have to make sure is that the ohm, the resistance section, is not meant to really handle voltage of any amount or amperage. Okay? So one of the things you always want to make sure is when you're measuring your resistance, never have the circuit powered up.
Oh, that'd be bad. 'Cause
Okay.
I think that would fry your multimeter.
It could, especially if the voltage is very high. Like we've talked, if you had 12 volts, for example, like a car battery, probably wouldn't be good for your multimeter. Could burn it up. Okay, so we always want to measure resistance with the power off.
Yeah.
Okay, that's different than measuring amperage, for example.
Yeah.
On this side, you have to have it on in order to measure that.
Yeah.
But for an ohm meter, the ohm meter functions, you want to have that off.
Yeah.
What instrument is used to measure resistance? A, an oscilloscope. B, a spectrum analyzer. C, a noise bridge. Or D, an ohm meter?
Can you talk about A, B, and C?
Okay, so an oscilloscope is something that we would use to measure a frequency.
Ah,
Okay.
that makes sense because it oscillates.
And it's
Oscillate
also,
is the word.
so only one of these devices have we actually used. Can you pick out which one we've actually used?
I think it's D, an ohm meter.
Right. A spectrum analyzer, some of these instruments are more higher end and you may not get a chance to use them.
Yeah.
Like I would really love an oscilloscope, but I can't afford one.
Oh, yeah.
What is impedance? A, a measure of the opposition to AC current flow in a circuit. B, the inverse of resistance. C, the Q or quality factor of a component. Or D, the power handling capability of a component.
I think my answer would be A measure of the opposition to AC current flow in the circuit.
Yep, you got it. There's some trickiness there because remember how we talked about that so impedance is kind of talks about both resistance and reactance. So they kind of trick you there a little bit because they're talking about resistance a little bit.
Yeah.
And you might be tricked into thinking that that's, those two things are kind of related because they are, but not in an inverse.
Yeah.
What is the unit of impedance? A, volts, B, amperes, C, coulombs, and D, ohms.
I would like to ask a question about C, coulombs.
C.
What does that mean?
I thought you might. C, coulombs is actually, it is a unit, but it's a unit that's related to the one above it, amperes. Okay? And we didn't really talk about that much in current, but coulombs is actually a measure of the actual charges that are, or the electrons that are flowing. Okay? For all intents and purposes, we don't usually talk about that as much unless you're really into electronics and that kind of thing. Okay?
So, ruling that out, I think the answer would be D, ohms.
Right. Because you've seen their other ones and you know what those ones are. Which of the following measurements are commonly made using a multimeter? A, SWR and RF power. B, signal strength and noise. C, impedance and reactance. And D, voltage and resistance.
Can you explain the A, SWR, and RF power?
Sure. SWR stands for standing wave ratio, and that is a topic that we're definitely going to get into on later videos.
Okay.
And RF power stands for radio frequency power. Okay. And so both of those have to do with waves, and transmitting waves.
But not with resistance. So I'm going to say D, voltage and resistance.
Good job. Which of the following might damage a multimeter? A, measuring a voltage that's too small for the chosen scale. B, leaving the meter in the milliamps position overnight. C, attempting to measure voltage when using the resistance setting. And D, not allowing it to warm up properly.
Well,
this one's a tricky one, isn't it?
Well, like we said in our hands-on, it would be, you can't measure volts or amps on the resistance setting, so it would be C.
Good job, you remembered. Yeah, what they're getting at there is that if you're measuring voltage, that means the power is on.
Yeah, you don't want the power on. That could fry
and
stuff.
It could damage the meter, like they talk about in the question.
Yep.
The other ones are not really.
Yeah. If you leave it in the milliamps position overnight, maybe all that will happen is your battery will drain out. And
it won't damage the meter. You just might have to change the battery.
Yeah, I've done that a couple times. Leave it on overnight.
Measuring a voltage too small for the chosen scale, that's not gonna be a problem.
Yeah.
And not allowing, you don't typically have to allow it to warm up properly.
Yeah.
And even if you found a multimeter that happened to need to warm up, which I've never run into the one that way, you still wouldn't damage it.
Yeah.
Which of the following precautions should be taken when measuring circuit resistance with an ohm meter? A, ensure that the applied voltages are correct. B, ensure that the circuit is not powered. C, ensure that the circuit is grounded. Or D, ensure that the circuit is operating at the correct frequency.
Well, like we just said a minute ago, we want to make sure that the circuit is not powered because that could damage our multimeter. So B, ensure that the circuit is not powered.
Good job. Keep the power off.